imagine a few more people will wander in as class gets going. So let's start just with a little bit of housekeeping, particularly because your final projects are coming up or coming up on the end of term. Your essays, essay number 5, I believe, were all really good, and it's really exciting to see how much everyone's writing has improved over the semester. I want to make just a quick note, because I noticed this in a couple different essays, where people would say, oh, this chapter used this kind of identification strategy. And particularly if you think about doing that in your final essays, that's great. I like to see you guys making these connections, but it's not enough to merely point out when a strategy is used or not used. You have to explain why. So a lot of people would say, you know, chapter 17 used instrumental variables, but didn't explain how it was an instrument, what it was instrumenting for. And I know that's a little tough on the biweekly essays where we don't have as much of a word count, but if you plan on writing about something like that for your final essay, just make sure I can follow your thoughts. And it's not saying that anyone was wrong for you know, saying this was a diff and diff, or this was an IV, or this was, what else did we do? You know, regression or anything like that. But when you talk about these strategies, you have to explain how so. From there, let's move on to how we'd like to start class usually. Anyone have any questions, comments, or concerns they want to bring to the class's attention moving forward? Yeah, so we are officially in spring. We are in week 11, although that's kind of misleading because without a spring break, we actually have 13 weeks of this term. But yeah, everyone think about your final projects, think about your last papers, not just in this class, but in all your classes. Let's finish this strange spring semester strongly. So with that in mind, today we're learning a new identification strategy. We're learning something called regression discontinuity. You might see this listed as RD or RDD. In the case where there's 2 Ds, the second D stands for design, regression discontinuity designs. And previously, when we've been talking about identification strategies, we've talked about experiments, we've talked about difference in differences, we've talked about just basic regression, and we've talked about instruments. And the idea behind all these different identification strategies, remember with instrumentation we talked about endogenous and exogenous. The idea with all these identification strategies, now that we have some vocab to talk about it, is to find plausibly exogenous variation to determine a causal effect. The idea behind everything we've done so far is to think about what is determined from outside the system so we can look at causes and effects, and in particular so we can look at the effects of causes. And what we want to know in particular is how can we rule out these sources of bias that we've been talking about. We want to know that selection into the cause is not determined within the system. So what we're doing today is just expanding on that by introducing our next strategy, regression discontinuity designs. And this is, again, one of those parts of Core 170 where the words are really jargony, but once we start to see the pictures, hopefully it makes a lot more sense. And of these words, regression discontinuity designs, you should already recognize a lot of them. In particular, you should recognize regression, which we already learned about. Just to revisit what a regression is, it's a statistical technique for describing a line that fits the data generating process. Linear regression gets you the line of best fit, which helps us to predict outcomes. So previously, we saw the example of predicting the outcome of test scores based on class size. And in predicting these outcomes, the deeper question that we're concerned with is how a change in one factor affects a change in another. So let's go back to that example. If your student-to-teacher ratio changes, if you add 1 student to your class, how is that going to impact student outcomes? Now, in order to understand this impact, we have to interrogate the assumptions of a regression. And what we found when we were talking about regressions in general was that we only get good, and I have good in quotes there, we only get plausibly causal regression results when unobserved factors are independent of our input variables. And again, that's really verbose, it's really kind of jargony, but let's keep going back to this example of class size, right? Because we had a lot of unobserved factors when it comes to class size. Who remembers when we're thinking about class size and test scores, what are some unobserved factors there? What do you guys think? Cynthia, is that a hand or a stretch? All right. So when we're thinking about student outcomes and we're thinking about class size, are there any factors that we're not necessarily observing that are related to those? Ashley, when we're thinking about class size and we're thinking about student outcomes, what factors are we not observing? Yeah, Emily. Okay, and do higher skilled teachers tend to land at, say, better school districts? Okay. Lily? Quality of the students? So is student quality related to class size in any way? Okay, so we've got teacher quality, we've got student quality. What else might be unobserved? Think about the classes you all grew up in. Yeah, Cynthia.
I would say even other classes that they're taking that's not being studied, because in some cases, other classes take more work and they take more focus, so the easier classes tend to go to the wayside.
Okay, other classes, great job. Remember, this is an example that we've already seen in our regression lecture. I'm not having you, yeah, Jackie.
Just going along with that, also like honors classes versus for AP classes versus regular classes.
Okay, so honors and AP classes might have different student to teacher ratios. It might, to Emily's point, also be related to inherent student quality, whatever that means. We'll punt on that for a little bit. What else? What might be unobserved in this system that's going to impact both student to teacher ratio, that's going to impact class size, and also test scores, this outcome that we're looking at? What about wealth? Do wealthier school districts tend to have smaller classes? All right. What about things like motivation? Is it easier to be a more motivated student when you can get individual attention? What about things like resources? We already said wealth. Maybe classrooms with more resources have smaller student-teacher ratios. They also have better test scores. Yeah, Elizabeth.
Wealthier school districts tend to have teachers that have a higher level of teacher preparation and academic degrees.
Okay, so Emily, earlier you mentioned teacher quality. So maybe teacher quality isn't the right thing to look at or the right word here, but maybe teacher preparation might be related to both class size and student outcomes. Why are we saying all this? Because when we studied regression, the problem was it was really hard to get good regression results because of this endogeneity problem. What we're doing today is introducing a way that this regression can be more plausible that you're getting good results. And that's regression discontinuity. Discontinuity is exactly what it sounds like. It's discontinuous. So you all remember from math class, when we think of something as continuous, we think if we put our finger on it and trace the curve, we never lift our finger up. If something is discontinuous and you're tracing a curve, you have to lift your finger up at some point. What does this mean in terms of Core 170? What does this mean in terms of decisions in a data-driven world? It means that in a lot of cases, there's some sort of forcing variable, some sort of cutoff variable that determines treatment assignment. The variable might be related to potential outcomes, but what we're assuming is that there's a smooth relationship for this variable except on either side of the forcing variable. And where there's this cutoff, there's a regression discontinuity. So think about in your own lives. Can you think of anywhere where there's a cutoff for something? Do any of you have cutoffs that you experience in your own lives? Cutoff variables. Yeah, Annika. Age restrictions. So you can't drink legally unless you're 21, but if you're 21 in one day, you look very similar to if you're 20 and 11 months. Chloe.
Well, for me, I have height restrictions.
Okay.
Like, for instance, if I were to like go to an ice skating show and there's a pony, or there's like a place, I can't ride them because I'm too tall.
Okay, so you might experience height restrictions in athletics? Yeah, Cammie.
And opposite of that, I can't go on some of the roller coasters at Disney World because I'm too short.
Okay. What else? What other threshold variables can you think of? Yeah, Elizabeth.
Like in athletics, when you have to like make a certain time or like, I don't know, something else to qualify for something.
Qualifying time. So let's say a qualifying time in one of your meets is 4 minutes. I'm just throwing that out there. A swimmer who swims at 4 minutes 1 second looks pretty similar to a swimmer who swims at 3 minutes 59 seconds, but they're just on other side of that cutoff. You mentioned athletics. Chloe, you mentioned athletics. We can think of other athletic-related cutoffs. Do you guys have to maintain a certain GPA to stay on the team? What's that GPA? 1.7, but does a student who has a 1.71 GPA look very similar to a student that has a 1.69 GPA? When you have these cutoff variables, we can get really interesting data descriptions because there's this smooth, continuous relationship between, say, student and outcome, but we have this forcing variable that puts you on either side of the cutoff. So the example I came up with before class is there's a smooth relationship between how much you have to drink and how drunk you are. But in Virginia, the legal limit is 0.08. So maybe someone driving drunk, driving with a legal limit past 0.08, looks like someone driving sober. They just happen to be on other sides of the cutoff. Questions so far? So like I was saying, previously we talked about linear regression, just this way of predicting with a line of best fit. And what we saw, and this is just a copy and pasted slide from our earlier lecture, what we saw was that with these data, students in districts with a student-to-teacher ratio of 15 have higher test scores on average than students in districts with a student-to-teacher ratio of 25. And we posited a lot of different reasons, like you all just did a few minutes ago, for why that might be the case. Certainly, we might think that lower student-to-teacher ratios, smaller class sizes, help with test scores. But we can think of a lot of alternative explanations for why that might not be the case, or why we might be capturing some sort of spurious relationship, why we might be capturing a different relationship, whether it's student ability correlated with class size, or motivation, or teacher quality, like you said, or wealth of the school district. That U term that we talked about in our regression lecture, we can think of as an error term. But more broadly, we can think of as an everything else term. And is everything else that we're not capturing, remember all we're capturing here is class size and test scores, is everything else that we're not capturing, does that look the same across students or different? And does it look the same for students in class sizes of 15 versus class sizes of 25? The problem here is that finding conditional independence, this thing that makes our regression output plausibly causal, this thing that makes our regression output good, for lack of a better word, is hard. There's a lot of unobserved factors in any data-driven decision that we're interested in that could be correlated with student success or whatever it is that interests you. Whether it's how fast am I going to swim this weekend, or how well am I going to do on this test, or am I going to get pulled over by the cops, or any other thing that interests you when it comes to making a data-driven decision, it's hard to find this conditional independence. There's lots of unobserved factors. When it comes specifically to student test scores, in other words, what that means is we need to find something similar to instrumentation, like we did last week. We need to find something that's uncorrelated with income, that's uncorrelated with motivation, that's uncorrelated with teacher quality, that's uncorrelated with the HVAC system in your school, any of those things, but that also determines class size. So can anyone think of anything that determines class size that's uncorrelated with any of those outcomes? I see no hands, and that's a good sign because it's really hard to think of these things. So let's take a sort of quick break and talk about this guy. Who knows who this guy is? You should tell Laufenberg that we talked about this today. This is Moses ben Maimon, more commonly known as Maimonides. He was a 12th century rabbinic and Talmudic scholar in Cordovan, which is modern-day Spain. And among the many philosophies that Maimonides is famous for, he's famous for reading the Talmud and coming up with what's known as Maimonides' rule. It says in his writings that according to the Talmud, 25 children may be put in charge of one teacher. If the number of the class exceeds 25 but is less than 40, you should have a teacher's assistant. If there are more than 40 students, you should have more than one teacher. We can put this in math terms. We can interpret this in a more modern context. Maimonides' rule says you shouldn't have more than 40 students in a one-teacher class. The maximum student-to-teacher ratio, according to Maimonides' rule, is 40. And the interesting thing is, though this guy was writing in 12th century Spain, Israeli school districts to this day use this rule that you should not have a maximum student-to-teacher ratio of more than 40. This has been law in Israel since 1969. It's been used to determine the division of public school cohorts. Everyone in Israel knows this rule, and importantly, their Ministry of Education, their Department of Ed, circulates these standing orders regularly. So everyone knows this rule, and everyone is regularly reminded of this rule. In other words, Maimonides' rule offers us a source of plausibly exogenous variation. It offers us a way to look at class size, to look at student-to-teacher ratio, without being related to teacher quality or student quality or motivation or academic ability or school district income or how good the heating and air conditioning system is in your school or anything that might also be associated with both test scores and student-to-teacher ratio. We have here plausibly exogenous variation. We have what's going to look like a discontinuous jump. What does this rule afford us? What does this get us, in other words? What do you guys think? What does this mean, that you can't have a maximum student-to-teacher ratio of more than 40? What does this mean? Yeah, Juliet. Okay, so we know that you're going to have a maximum student-teacher ratio here. And this is interesting because from that California data we put up a minute ago and we saw in an earlier class, we know that class size is negatively correlated with test score. Higher student-to-teacher ratios have, on average, worse test scores. But we don't know what's causing this. We don't know whether it's the teachers themselves or if it's these unobserved factors. But we have this rule all of a sudden that determines class size. It's no longer how wealthy your school district is that's determining class size, or how good your teachers are that are determining class size. We have a rule that determines class size, and that rule is pretty simple. If you have 39 students or less, there's one teacher. If you have 40 to 79 students, there are two teachers. If you have more than 80 students, there are three teachers, and so on. And what this is going to look like is this predictable seesaw-like graph. I'll show you the seesaw in a second, but this is important because we already knew that class size was negatively correlated with test score, that student-to-teacher ratio was negatively correlated with outcome. Questions so far? So let's see what this rule looks like in practice. Let's see this predictable seesaw image. On that horizontal axis, on that bottom x-axis, we have school enrollment. On that vertical axis, that y-axis, we have class size. So it's important to take a minute to think about the difference between school enrollment and class size. Enrollment is the whole cohort. So where I went to school, elementary school that is, there were 3 third-grade classes. I did not go to elementary school in Israel, but if I did, 3 third-grade classes would imply that you had more than 80 students in 3rd grade. And we see that in this seesaw graph. If you have 0 to about 39 students, it looks like the class size tracks enrollment linearly. As soon as enrollment passes that threshold, class size drops down by about half, predictably goes up, drops down, and so on and so forth. Now, it's important to note that not every school district can follow this rule exactly. So what we have on these graphs, I don't know if you guys can see, is the actual enrollment and the enrollment predicted by the rule. And not every school district can follow these graphs exactly. But it looks like the enrollment, the class size, is pretty tight around the prediction. There's some variation around the rule, but we generally follow the predictions quite well. Here we have graphs for both 4th grade and 5th grade. So what makes this a discontinuity? That we have these jumps around the cutoff variable. And I've highlighted the cutoff variable in red. So at each 40 student chunk, 40 student enrollment, we see that class size dramatically drops down because they hired an additional teacher. Questions so far? Why is this important? Why do you guys think? Why is it important that we have this rule in Israel that's determining class size? Yeah, Riley. Okay, that might be a good reason to be concerned with class size overall. But I'm talking about in terms of the data, why is it important? Why is it important that we have this rule? Yeah, Elizabeth. Right, exactly. For anyone that didn't hear Elizabeth, it keeps the other variables that we're worried about from influencing this predictor variable. Remember, when we say identification, what we mean is ruling out alternative explanations. So let's talk about the idea here. And it's the same thing we were talking about a minute ago with your GPA cutoffs, with your BAC cutoffs, with your height cutoffs, with your qualifying times in a swim meet. A school with 39 fourth grade students, on average, probably looks pretty similar to a school with 40 fourth grade students. But we have dramatically different student-to-teacher ratios because of this rule, even though those two schools on either side of the cutoff probably look very similar to one another. Put differently, we're ruling out alternative explanations. We're ruling out the dependence of you. We're ruling out all these other things that could be influencing class size or student-to-teacher ratio. Does anyone want to push back on this? Why might that not be the case? And so we might see some reasons later in class why we can push back on this, but the important thing here is this is a local effect. This technique, this discontinuous technique, is really good for comparing things that are really close to either side of that cutoff variable. For comparing a student who doesn't go on academic probation with a 1.69 GPA, 1.71 GPA, to one who does go on academic probation with a 1.69 GPA. It's a local effect, either side of that cutoff. This technique is not very good at comparing a student with a 1.5 GPA to a 4.0 GPA. Despite the fact that those students are on either side of the cutoff, we might think that they are very different. We might think there's a lot going on there not related to the cutoff. What we're looking at here is this very local effect. Schools that we think look similar to one another, but it just so happens through blind luck that one happens to be on the other side of the student-teacher ratio cutoff. So let's see what actually happens in the data. So let's talk about unemployment assistance. What is it? Who knows? What's unemployment? Yeah, Renee. Right, exactly right. It's temporary financial assistance to individuals who become unemployed through no fault of their own. You don't get unemployment assistance if you get fired. You get it if you get laid off. Why might this be a good thing? Juliet. Okay, so it creates a buffer. Why else? Why might this be a good thing? Yeah. Okay, you're helping out people who are down on their luck. Why else, Elizabeth? Might prevent homelessness. That might also be good for other people like landlords, making sure they get their rent checks, etc. Why might it be a bad thing? What are some of the arguments against it? Certainly this is a hot button issue. Yeah, Riley. Okay. Okay, so maybe it serves as a disincentive to work. What else? Yeah, that's pretty much what I came up with. The arguments in favor is it helps people who need it. It keeps demand up. The arguments against is it serves as a disincentive. To your point, if you're getting money from the government for free, maybe you have incentive to try and cheat the system. Maybe you have disincentive to look for a new job. Of course, all these things that we're positing, both these arguments in favor and arguments against, are just suppositions. It's our job as people working with data to test these theories, test these hypotheses. So how might we test this? Well, just like last week when the question, how might we test this, was always answered with an instrumental variable, today the question of how might we test this is always going to be answered with a regression discontinuity. Let's come up with an interesting discontinuity that might be a little less political to the rest of us. In 1988 in Austria, the steel industry collapsed. Austria in the late 80s, big steel industry, it collapsed. They had unprecedented unemployment. And so in response to the collapse of this industry, because people were down on their luck, because we needed to prop up demand, because we wanted to prevent homelessness and any number of other things, the government extended unemployment benefits from 30 weeks previously to 209 weeks of unemployment assistance. What makes something a regression discontinuity? There's one thing that we talked about that makes it a regression discontinuity. What's that? Yeah, Jackie. Cutoff variable. The government extended benefits from 30 weeks to 209 weeks for people over 50. Not everyone got this extended unemployment benefit, just people over 50. Because it's probably hard for people over 50 to go back to work, particularly these people who are steel workers and not, say, trained in high tech. How do we know if we have a regression discontinuity? If there is this discontinuous jump. There's some cutoff variable, in this case, how old you are, and there is a vast difference in what happens. So if your class size is 41, your student-to-teacher ratio drops. If you're over 50, you get a whole bunch more weeks of unemployment. So what did we find in this data? We found that the duration of the job search was prolonged by at least 0.09 weeks per additional week of benefit for men. For women over the age of 50, it was prolonged by at least 0.32 weeks. So we want to know, does unemployment insurance serve as a disincentive to work? We want to know if these arguments against unemployment assistance are bearing water. And in Austria, in the late 80s, there was a lower retirement age that applied to women. So it makes sense that women might have more prolonged bouts of unemployment when you extend their benefits. Why is that? Because if you can extend your benefits just until you reach retirement age, then you can retire and everything will be fine. But we should also note some other things, which is if we thought people were trying to cheat the system, or tweak the system, or game the system, or if we thought there was a disincentive to work, we would expect those numbers to be much higher. If we thought extending your benefits made it so you didn't want to find a job, we would expect extending the benefits by a week would extend your bout of unemployment by a week. But those numbers are much less than 1, which suggests that we're doing exactly what we set out to do. Help people out who are down on their luck, prevent homelessness, boost demand, without worrying too much about whether or not people are gaming the system. But of course, to draw those conclusions, we've made some assumptions. What are some of the assumptions that we've drawn? What are some of the assumptions? We've already talked about them a little bit. This is just a quick review. Well, we talked about continuity as an assumption. A worker who is 49 years old and 6 months probably looks like a worker who is 50 years old and 6 months in Austria in the late 80s. The only difference is they happen to be on other sides of that cutoff line. The identifying assumption here, the thing that allows us to rule out alternative explanations, is this continuity assumption, which is kind of weird to say because we're talking about discontinuous jumps. But that's exactly why we have this continuity assumption, that in absence of the rule, in absence of the cutoff, the treated subjects look like the untreated subjects. Swimmers swimming 3 minutes 59-second laps look like swimmers who are swimming 4 minute and 1 second laps. Athletes who have a GPA of 1.71 look like athletes who have a GPA of 1.69. School districts where you have 39 fourth graders look like school districts where you have 41 fourth graders. The continuity assumption says that expected potential outcomes would change smoothly were it not for the cutoff. In other words, it's really this change in policy that's driving the effect. So what are some problems with this framework? You guys are leaders. You are learning how to make decisions in a data-driven world. Why might these identification strategies lead you astray? What are some potential problems with the regression discontinuity framework? Peyton, what do you think? What are some problems with this framework? Okay, so maybe it's not true that a 50-year-old worker looks like a 49-year-old worker. Maybe continuity is a problem. What else? What might be a problem with this framework?
Under the assumption that 50-year-old people don't necessarily have the drive to work, like it's assuming that a 50-year-old person isn't going to put forth the effort to find a job.
Okay, so when I say what are, excellent point, let's see if we can generalize that. Because when I say what are the problems with the framework, I don't just mean the unemployment example. I mean regression discontinuity as a design overall. So yeah, maybe there's a problem with the policy that spurred the cutoff. Excellent point. Elizabeth.
There might be some variables that impact the data that are not eliminated with cutoff variables.
Okay, what do you mean?
I don't know. I was just thinking that there are probably some things that go along with that. They could influence the data, like maybe if it's like regional or something.
Okay, excellent. It sounds like you're saying something similar to what Peyton was saying, which is maybe continuity is an overly strong assumption. People on other sides of the cutoff might not look very similar to one another. Maybe the cutoff, like you said, is regional, and people in Indiana don't look like people in Illinois, for instance. Excellent point. What else might be wrong with this framework, or problematic, let's say? Yeah, Renee. I'm sorry, I couldn't hear you. Could you say that again? Excellent point. So if I heard you correctly, it sounds like the determination of the cutoff might be based on something that's happening within the system already. So certainly not every school district abides by Maimonides' rule. Maybe if there are cutoff variables in, say, San Jose, California, that cutoff variable is going to be determined by something unique to San Jose. You're going to have an endogeneity problem. Excellent point. What else? So you guys are all, I think, spot on. I want to know a little further, which is we might have some sort of selection effect, right? If you know the cutoff rule in advance, you could tweak the system a little bit. If you, say, are interested in getting additional unemployment and you are aged 49 and 11 months, maybe you wait a month to apply. if you are a student athlete, maybe you want to do something to tweak your grades so that you don't get academic probation. One of the problems with regression discontinuity as a design is that cutoff rules are well known and well publicized, and people have incentive to adjust around those. Not just well known and well publicized, but oftentimes there's a lag between when a policy is announced and when a policy is enacted. So people have time to adjust their behavior as a result. Elizabeth, Peyton, Renee, to your points, maybe the cutoff is endogenous to factors that independently cause potential outcomes to shift. Or maybe there's a reason why we see people on either side of the cutoff variable. So Kim and Chloe, let's take your example of height. Maybe there's biological reasons why people tend to be certain heights. That's non-random. That's going to influence the running variable, the predictor variable. We can think of several examples why this might be the case. Whether it's taking an exam more than once. So suppose you get a financial aid benefit at certain SAT scores. We might see people taking the SAT more than once. In fact, in our bias lecture, we talked about college campuses that do just that because SAT score influences US News and World Report rankings. Maybe on things relating to aid where you get more or less aid at certain levels, you self-report your income differently. Maybe there's some unobservable characteristic change that happens at the threshold that has an impact on the outcome. To your points from earlier, maybe the cutoff variable is endogenous. We can think about this in policy. What about the difference between someone who gets charged as a minor when they commit a crime versus someone who gets charged as an adult? In this case, the age threshold triggers the treatment, higher penalties for crime, but is also correlated with variables that influence the outcome, such as graduating from high school and voting rights. So maybe the fact that there's a cutoff suggests that there's already an endogeneity problem. So we have this really powerful identification strategy, these discontinuous designs, but it's our job as leaders, it's our job in Core 170 to push back against what makes these identification strategies powerful. Questions so far? All right, well, that's it for this time.